Welcome back to the course on superconductivity. Today we're going to talk about temperature gradient in a cooling system. We'll first define the heat transfer types, then define what a temperature gradient is, and finish by looking at an example in a cooling system. First, there are three types of heat transfer: conduction, which is the heat transfer through direct contact; convection, which happens because of the movement of fluids; and radiation, which is the heat transfer through electromagnetic waves. It happens for all objects, but usually is smaller than the other two types at room temperature or below. Note that radiation is the only heat transfer that can happen in a vacuum. A temperature gradient is a difference in temperature per unit length. The shorter the distance and the higher the temperature difference, the higher the temperature gradient. On the left-hand side graph, we have a difference in temperature between the left-hand side of the wall, T1, and the right-hand side of the wall, T2, separated by a distance delta. This is a thermal gradient, therefore heat is going to flow from the higher potential, T1, to the lower potential, T2. The heat transfer equations for each type are as follows. In our case, we consider only conduction since we have a solid wall, so there are no fluids moving and the radiation cannot go through. However, in most real systems, the three types of heat transfer are happening simultaneously. Also, pay attention to the law for radiation that scales to the fourth power. This shows how the radiation heat transfer is usually very small compared to the other types, but can become dominant at higher temperatures. As introduced before, there are three types of cooling methods. The bath or dunk cooling is often used for its simplicity and high stability, though it uses large amounts of cryogens. The forced cooling method uses less cryogen and grants control over the heat transfer rate. However, it is much more complicated to use and requires a pump. The conduction cooling method is easy to implement and requires only a cryocooler. Here is a typical example of two cooling methods that use a second stage to reduce the temperature gradients. On the left-hand side, we have a helium bath thermally protected by a nitrogen bath. If the nitrogen bath wouldn't be there, the temperature gradient would be very high, from 4K to 300K, and helium, having a low latent heat, would be consumed at a high rate. However, with this two-stage bath, there is a low temperature gradient for the helium bath and the highest temperature gradient is between the liquid nitrogen and the outside. Therefore, we will consume much less helium. For the conduction method, the same principle is applied with a two-stage cryocooler. To conclude, by definition, temperature gradients are the differences in temperature within a system. They cause three types of heat transfer: conduction, which occurs through direct contact; convection, involving heat transfer through fluid motion; and radiation, where heat is emitted through electromagnetic waves. High temperature gradients happen in cryogenic systems and must be limited to have an efficient cooling system.